So this is the case. We have a voltage source, can also be a current source. But in this case, I selected the voltage source with a series resistor, and we want to know and of course, we want to have the total noise in series because we want to have a voltage representation. The resistor RS itself also generates noise, of course. This should be later on included in this VN. And the question that we are trying to answer here is the following. If there is an optimum for the noise, so if we can design the FET in such a way that we have the lowest possible noise, so the best possible noise figure, then if the requirement would require a better noise figure, we found a showstopper, which means you cannot design it in the process. That is very important. So you don't need to try. If we know that the optimum is not available, is not good enough, I mean, if an optimum is not good enough, well, then it cannot be made. And we will find out that probably you need a process with a higher FT because the optimum will be related to the FT of a process and the maximum frequency you want to operate at. I don't do all the formulas and all the derivations from the book because that's quite boring. You can read it yourself. But I want to show you how it goes. So I want to show you the process and the differentiation and integration and whatever is needed. You can do it yourself. But I want to show you the process and the conclusions so that you understand that there is an optimum. And if this optimum is not good enough, then it cannot be done. As simple as that. So Vn is the total source referred noise that we want to know. And if we look to the equations we found before, we have the Vn is 4kTRS. That's now what we added. That's the noise of the signal source itself, plus this B plus D times R, as it was ZS before when there was an impedance, but now we selected a resistive source, and then squared times the spectral density of the intrinsic FET current noise, current channel noise. We know B and D, so we can even go further in this expression, and then it looks like this. And in this spectrum of ID, this SID, there's also 4kT, gamma n divided times GM, sorry. So we can combine the 4kT over all the terms and find first I write the other one, I do the squaring of magnitude I do, and then I will substitute the result of SID. So here we find 4kT times, well, the noise of the resistor itself, and gamma divided by GM, which is a kind of resistance that equals approximately 1 of GM. So you can already say you put like 1 over GM in series with the signal path. And here is a high frequency part. A high frequency part due to the gate-induced noise. Now, what you can see in many books and other lectures is they say there is no optimum. Because if you do more current and a wider transistor, you can make GM as large as you want. And then this term, N times gamma divided by GM, drops. In the limit, it would become 0, but it means you could make any noise figure because you can get it arbitrarily small with respect to RM. So there is no optimum. But that's not true. Because if you do so, you also do something with the gate-induced noise. And therefore, it is interesting to look at a frequency plot of those contributions and see what we are doing actually. So here, I made a frequency plot. You see that it's quite a noisy situation because the FET 4kT and gamma divided by GM is much more than 4kT RS. But okay, it's just for the picture. So you see 4kT RS is a source noise. The second term N gamma divided by GM times 4kT is this upper line. And then this line that increases with frequency is the gate contribution of the gate induced noise. Now let's see what we can do if there is some, and sorry, between f min and f max is the frequency range of interest. What we are going to do is we are going to scale the width with the current. And I hope you remember from the previous lecture that that means that we maintain the inversion coefficient. And if we maintain the inversion coefficient, it means that GM is proportional with the width. So if GM is proportional with the width, then it means that the upper line, 4kT n gamma divided by GM, will go down. And the upper line there you see GM is in the numerator, will go up, which means that the corner frequency, FC, comes to a lower frequency if we increase the width. Now you can increase the width so far that this corner frequency always becomes part of your frequency range of interest. Just make the FET wide enough, of course, scaling up to a huge current maybe. But we are talking here about showstoppers. So I'm not talking about is it possible to make this for 1 milliamp or for 1 microamp? No. Is it at all possible in this process? That's the question that we are asking if we are investigating showstoppers. Not the price. Whatever price you would like to pay in this process, area or current, power dissipation, if the value of the noise figure is too large in the process, if it will never become low enough, then there is a showstopper. So we see if the width increases, that is upper line 4kT and gamma divided by GM will drop. The gate induced noise will increase and the corner frequency comes to a lower frequency. Now you can imagine if the contribution above this corner frequency equals the contribution to the RMS value below, then we are in a kind of balance. But if I would go further with the increase, then I would have more high frequency noise and less low frequency noise, but the total integral will be worse. So that is, I expect from this picture already that there will be a kind of optimum. An optimum in which probably the contribution above the corner frequency to the total RMS value of the input noise voltage is equal to that of the lower frequency range. So that is the design question, is the analysis question that we have now. Is there an optimum and can we calculate it? Well, here I put it again. How do we calculate the RMS value? You integrate over the whole frequency range. Well, this is a square, just a mean square value. The root of it is a root mean square. So I didn't do that. Just keep this one. That keeps the equations a little bit more friendly. And now I did something here. I said, well, at some value of I and GM, I call it just a reference value like GMO. I have a certain width, WO, and here I let GM scale with the width. And here I do the same. I let GM scale with the width. So GM is GMO times WO divided by W in this case. So W divided by WO here in the letter one. So you see a 1 over X and a proportional function. And well, the optimum of such a function is exactly when this contribution of the 1 over X equals the other one. But you can also simply take the derivative and calculate it. And from that, you find an optimum width. An optimum width for the device. And with that width, we could calculate the noise factor, the total noise, and then we have the showstopper value for this frequency range in the process. So you find this one, the definition of the noise figure is, of course, the total source referred noise divided by the noise that is only coming from the original signal source. That is the definition of the noise figure. So the total is here in the above in the integral, and the other one is here 4kTRS times b, the bandwidth, which is f max minus f min. So I'm not going to substitute. You can do it yourself, but you can realize this is how we calculate it. And the lowest vacuum value can be obtained at the maximum inversion coefficient and an optimum device width. Maximum inversion coefficient, that means that we are going for the highest possible GM at some width. And of course, you know now from the presentation of the behavior of the FET that the highest possible value of GM, well, if you go above critical inversion, it's no use of increasing the current much more. So then you are only increasing current, but you don't get GM for it because GM versus current curve flattens out. That's what you can see with this Jupyter Notebook tool that we have given you, but also in the graphs that you found in the book and in the presentation. So if you want to have a quick investigation whether a certain noise figure for a resistive source can be achieved, yes or no, you design your FET at critical inversion, you calculate this noise figure for the frequency range and your optimum width that you found from the above equation. And this all can easily be done in SlideCap